Hi, my name is Allison. Today I'm going to be talking to you about enterprise storage and SAN data collection and measurement.
Our learning objectives today are to understand the available storage performance measurements, to describe some of the data collection approaches, and to understand key storage performance measurements. When we talk about the components of a SAN infrastructure, what I mean is we're discussing all of the components within the infrastructure, including the servers, the switches, and the storage arrays. In this section, we will discuss the servers. Let's take a look at the server just at an overview level. The server connects via host bus adapters to switches, which connect to the storage arrays and the LUNs or the storage on the storage arrays that are made host visible. From a server perspective, you can look at the throughput and the IOPS, and occasionally, depending on the platform, the utilization of the host bus adapter. You can also take a look at the disk or virtual paths and the throughput, the IOPS, and oftentimes the end-to-end response time. From the perspective of the server and the LUN, you can often get the read and write throughput and I/O rates, and occasionally you can get the response time, depending on the platform. From a Unix perspective, the application will access a file residing on a file system, and typically that's mounted on some kind of logical volume, which in most cases is coming from a logical group of storage called a volume group. And within that volume group, there are host virtual disks, or what the host believes to be physical disks, that actually point to external LUNs. Those external LUNs are coming from storage pools, which reside at some level on some type of RAID formatted disk drives. So that's an overview of the logical components from the server perspective. Let's take a look at the VMware architecture. In the VM architecture, you're going to have virtual hosts, and these virtual hosts have supporting files such as the configuration file or the .vmx file that is a descriptive file that has metadata about the actual VM configuration. And then you're going to have data storage that are going to be on VMDK files. And those are like your virtual disks on VM. And all of those things are going to reside on VMFS volume. And that VMFS volume is contained in a container called a data store. Now, that VMFS volume comes typically from external storage, such as Fibre channel SAN external storage LUNs. And those LUNs are provisioned to the VMware ESX host, and then that host uses it to create a VMFS volume, which is used in a data store to provision virtual disks to virtual hosts. Is it possible to look at the HBA performance? Well, the HBA statistics are provided to some extent via the vendor tools such as the QLogic SAN Surfer, the Emulex HB Anywhere, and those can be used to measure the IOs per second and the throughput or bytes per second. You can also refer to OS or operating system tools such as IOStat, SAR, perfmon on Windows to provide direct and indirect measurements of the IOPS throughput and response time for all of the associated drives, and those can be rolled up if you know the configuration information. I know AIX IOStat-A and then uppercase DR does provide information about the performance for a particular virtual adapter on a VIO server, or if it's a standalone LPAR, you can also get the adapter information directly. So what can be measured at the server logical volume level? Typically this is appropriate for Unix systems running either a native Unix logical volume manager or something like Windows Disk Manager, and these are the logical disk or logical volume statistics. A couple examples here. The AIX LVM can be measured through a tool called LVMstat, and you're going to get things about the IOPS and the throughput to the different LVMs or to the different logical volumes. And you can also run FileMon. And FileMon, what it does is it post-processes particular hooks from the trace facility, and it gives you information about very detailed activity for the files. So you get things like read and write response times, writes, reads, throughput, and you also get activity about how random and how much sequences you're having to access for every file access. So it's very detailed, low level kind of stuff. And for those that are running like a Veritas file system, you can use VxStat and get volume information, including the read and write, throughput, and response time. On Windows, if Windows is the platform, then you can use perfmon to gather logical disk information. And the logical disk are the partitions like the A, B, C, D, etc. partitions. And from these you can get important things like throughput, rates, and the response time. What can we measure at the server disk level? Well, it depends on the platform, but almost every platform on the market has utilities to look at the performance, both the response time, the latency, as well as the IOPS and throughput for the disks that are on the system. And this table contains a summary of the key performance metrics. Some operating systems actually have queuing metrics, which can also provide a really good indication of how much time is being spent waiting on the host before the IO is sent. And this can, especially in a virtualized environment where you have more than one host accessing the same LUN, external LUN, through something like a data store, you can get indications with the queue time of whether or not that access point is saturated on the host. And lastly, it's important to understand how multipathing affects the ability to get real clear visibility from the measurements. So really what you're seeing these days is that most of the pathing information and the ability to see from a host perspective the performance for the different paths, that, to save you trouble, they've kind of hidden that from you, the operating system makers have. So for the most part now, all the native multipathing IO pathing software hides the individual path statistics. There is an example given for Solaris running Veritas connecting to, this was an IBM SVC, where you would get individual path statistics. And what's nice about that is if you have them, they can tell you if you're getting better performance on one path than the other. And if that's the case, you can start looking along the path that appears to have the saturation and understand whether or not it's a fabric or front-end port on the downstream path. Also, it might indicate that the host may have host bus adapter contention if it has more than one HBA and you're having poor performance or latency on one of the paths. This table summarizes the ones where you can get the information for, and unfortunately, as we move forward, you're going to see less and less visibility into the individual paths. So let's just summarize the server measurement. Servers connect to the switches and the storage using HBAs. We can get information about that HBA, but it's going to depend on the manufacturer. We can also get information about the nature of the workload, whether it's IO bound or not, using the native tools. And we can get information about logical volume and physical or virtual disk performance. Most of these have latency as well as the throughput and rates. And then lastly, the multipathing software can actually mask the individual path statistics, but if they're available, they can be helpful in troubleshooting performance issues. In this section, we're going to look at the SAN fabric and its measurements. What is the SAN fabric? According to Wiki, the hardware that connects workstations and servers to storage devices in a SAN is referred to as a fabric. The SAN fabric enables any server to any storage device connectivity through the use of fiber channel switching technology. Let's take a look at the fabric and the measurement of the fabric. Most fabrics have edge switches in which hosts connect to, and then those edge switches connect to the core switch via ISLs. Most commonly what you'll see is storage hanging off the core. In some cases, particularly legacy environments, you may also have dedicated storage switches. These edge switches and storage switches connect to the core fabric via ISLs. And ISL just means intra-switch link. These are the E-ports on the switches. The way that it works is you'll have a host that connects to the edge through the core and back to the storage ports. And what we can do is we can measure the port throughput and the number of packets that are being sent. For end-to-end I/O traces, special equipment is required. There are several approaches to measurement. Using native interfaces such as CLI or logging on to the switches, you can actually run proprietary vendor-specific commands to get the data. Another way to get performance and error data is through the SMIS. And this will give you things like read and write packets and throughput and errors. You also might want to use SNMP. SNMP has been around for a long time, and it provides similar information to what you can get through SMIS. These are both subsets of what you can get in the native interfaces. And then lastly, there's specialized hardware that is available that can actually passively read the packets and analyze them. There is some overhead, at least in terms of performance. Usually that's outsourced to some kind of an appliance and does require additional hardware to perform that type of analysis. Let's take a look at some sample port data. Switches typically provide statistics like what I'm showing in this table, and these are available through SNMP, SIM/SMI, and the tools tend to average these over a period or provide graphing over time. For most tools, you can set thresholds. So let's take a look. We've got a fabric with some switches and some vSAN IDs, some port names, the speed at which the port is set to, and then the average number of packets received per second, the average number of packets transmitted per second, the peaks received, the peak sent, and then errors and discards. So this is a typical type of information that is available through any of the APIs. I know we didn't cover all of the possible measurements, but one of the questions that's important to ask is which mechanism is appropriate. And so there's a few ways to look at this. In this table, I outline some of the attributes. So for the native interface, the cost is low. It's included. The granularity is typically low, minutes or seconds depending on the switch. And it's a general purpose tool. So you can get any of the data you need. Sometimes the vendors actually provide some additional tooling around the measurement to do historical trending and graphing and set alerts and things like that. You can also use SMIS. And the cost is depends. It's basically open source, but it does take some programming experience. So in terms of the granularity, the design is really around minutes as opposed to seconds. It's a general purpose and it suits all environments if SMIS is something that is supported in your environment. In terms of SNMP, the cost is low. I mean, you can basically pick a number of open source SNMP software to look at the SNMP MIBs that are available for the different switches, and the granularity tends to be around minutes for trending and performance data, and alerts can be more granular. They can be as an event occurs. So these are both general purpose types of tools, the native SMIS and SNMP, although for all of those you need some kind of management tool around them. And then lastly, the packet trace. And the cost for these is generally high. You generally need to purchase additional hardware and software to do this. The good news is that it is sub-second. So if you're doing some kind of debugging for some kind of device driver or application performance issue, it is possible to gather that information with specialized hardware. To summarize SAN fabric and its measurement, a SAN fabric consists of one or more switches used to connect servers and storage. From these, we can measure with any basic tool, such as native tools, SNMP, or SMIS, the throughput and the I/O rates for each port, and in some cases, the port cards and fabric paths. There are specialized tools available that can read and correlate the fiber channel packets, but this does require specialized hardware and software. Measurement can take place via native tools, standard tools based on open standards, and specialized hardware. In this section, we'll take a closer look at the storage system measurement. When we talk about the storage system, what are we trying to measure? We really want to know if there's any component bottlenecks within the storage system. So this includes things like the front-end adapter utilizations, the front-end port throughput and utilizations, the way that the cache is behaving and information about the cache. We also want to know about the back-end device adapter or disk adapter utilization, and we want to know about the back-end disk drive performance. So we can easily get the storage system level I/O throughput and response time, and we'll often see correlation like we do on 9/13 at 4 a.m. But then there might be a later period like 11 a.m. where there's not really any correlation. So it's important to have the ability to drill down further into the storage measurement. So as we walk through the storage system components, the front end consists of the connectivity to the host, and that is the first thing we want to look at. So is the front end connectivity overloaded? We can look at several different things here. We can look at the ports and we can look at the front end adapters. Some architectures, as we discussed earlier in the architecture presentation, actually have dedicated hardware for front end adapters, and then other manufacturers use more general purpose processors for general tasks with specific threads assigned to specific cores for processing front end traffic. The thing that we want to know is how busy those adapters are, or the processors associated with those adapters. And in theory, we could get that by multiplying the I/O rate times the service time for a crude estimation. Unfortunately, we don't always have the service time, so we need to look at vendor-specific clues such as write delays or queue lengths, things like slot collisions, and cache hits if there's caching that we can get reporting on the front end. In terms of the front end ports, we can also get things like IOs and throughput, as well as response time for some platforms. We usually have the throughput capacity, but it's typically overstated. So it's good to be cautious when estimating bandwidth utilization or even the capabilities of the throughput of a particular set of ports or adapters, as it's often much less than the sum of the specification of the individual ports. So almost every platform does provide the read and write throughput for the front-end ports. In this case, it looks like it's a IBM DS8000, in particular DS8700. And we can see that 8 of the ports out of the associated 32 ports that are available are doing most of the workload. The port read response time shows that there really isn't any stress on the front-end ports. They're all having peaks less than 0.5 milliseconds. So as we move through the controller, we want to look at the cache statistics. So there's different things that can help us understand how effective the cache is behaving. For platforms like EMC, the EMC deferred write IOs provides an indication of whether or not the write cache is constrained. On IBM, the write cache delay IO, or fast write bypass, provides an indication of whether or not there's a problem performing fast writes to the cache. For the read effectiveness, we'd want to look at things like the read hit IOs per second over the read IOs, which gives you a read cache hit perspective. And that's a similar statistic available for all of the major platforms. In this case, we're going to look at the cache fast write bypasses or cache fast write delays, depending on the type of system. In this case, it is a fast write bypass, and these are for SVC systems. So what it means is writes do not hit the SVC cache, they go directly to the backend storage. If this was a storage controller, the writes would bypass the cache and go directly to the actual disks. Let's take a look at a sample read cache hit chart. In this case, we see several lines. Each of the lines represents a different disk storage system, and the y-axis is from 0 to 100. The x-axis is over time, and in a read hit percentage cache chart, we actually want to see higher numbers. Higher numbers indicates that more of the read IOs are being satisfied from cache. So a lower number, like the line in blue and the 2 different blue colors and then the yellow, those are indicating that those controllers are having lower read cache hit rates. So what we do with the IntelliMagic Vision is we actually have built-in thresholds for these, and then we rate how well or how poorly a storage system is doing. And then in the legend, we're going to highlight those controllers that are having issues and allow you to drill down for more detail. As we move from the cache to the back end, oftentimes disk storage systems have back-end disk adapters, and they'll either have general purpose processors that dedicate certain cores to the processing of the data movement between the disks and the cache, or they'll have specialized adapters that are designed to perform the RAID calculations and to provide buffering between the disks. And on the connection side to the disk, it's either fiber channel or SAS connections. We really want to know how busy the back-end adapter is. So if it is actually a dedicated kind of piece of hardware, we want to know how busy the processors are. We're not always going to have statistics that show us that. We could do some calculations with utilization like we did for the front end, which would require the IO rate times the service time, but we usually don't have the service time. So we can do things like estimating the throughput capacity based on the throughput specifications, and we can estimate the bandwidth utilization really by looking at the throughput divided by the capacity and multiply it by some conservative number like 0.8 or 80%. So there's different ways to look at how busy the back end is. Really what you want to find out is if you've got imbalances across the back end. Most controllers do a pretty good job about balancing the hardware across the back end. In this example, we'll look at the back-end utilization. This is provided by EMC, Symmetrics, and VMAX system. In the legend, you can see the different disk directors or device adapters, and you can also see the location, so which engine they're on and essentially which core they're tied to. That's the A, B, C, D information. So that's a little bit about an example of a disk director. In IntelliMagic, we actually rate these so that you see if there's an issue fairly easily. This is green, so it's good. And attached to the device adapters or the disk adapters are the actual disk drives. The thing that we're looking for here is how busy they are, and so that would be referenced by the utilization. Oftentimes utilization numbers are provided, and on many systems we can get things like the queue depths and the service times to indicate if we have disks that are overutilized and also if the disks are imbalanced in terms of the I/O distribution. In this chart we have the average disk utilization by tier. We've got nearline, we've got fiber channel, and we've got SSD drives. And what we're looking for is we want to make sure that none of the drives are spending too much of their time above 50% utilization. That's just kind of a good rule of thumb. And for IntelliMagic Vision, we actually rate these charts so that you can quickly see if there's anything above. In this case, the 3 terabyte drives spend a fairly significant amount of time in the busy zone. So if that's important to you, if it's during a time period that you care, then it might be something where we need to look at the way that the auto tiering is set up or add additional drives for that tier. In this case, we look at how well the I/O is balanced across the different drives. Now, for a system like HP 3PAR, this provides a really good indication of how effective the auto tiering policy is working. So we can see in this case that the average IOs per second for the 450 gig drives is around 150 IOs per second, whereas the 900 gig drives that have the same performance capabilities are running at about 50 IOs per second. So while we do see some of the SSD drives running higher than the 450 drives, overall, we see a disproportionate amount of work on the 450 gigabyte drive. So this is actually something where we'd want to go in and adjust the way that the auto tiering is working. And just to recap the RAID groups are formed from more than one disk, and they're formatted as some type of RAID, be it RAID 1, 5, 6, or 10. And they tend to provide response times, read and write throughput, and I/O traffic. What we have here is a sample of a RAID group write response time, and typically the RAID groups, they're on the back end, and the measurement is on the back end from the point of view of the device adapter. So we're not usually overly concerned about response times higher than what we would see on the front end, but we do want to make sure that we don't see a consistent and long periods where the response times are much higher than they are on the front end, as it indicates that the actual underlying disks are overutilized. A storage pool consists of one or more RAID groups, and we can see if we aggregate the backend data from the storage groups, we can see things like the disk utilization, the throughput, the IOPS, and if we want to aggregate the volume data on the front end, this is a good place where we can aggregate, and we can get things like the front end volume response times, IOPS, and throughput. In this case, we've summarized the write response time for all of the volumes in each of the pools and aggregated them. And what we can see is the front-end write response time by storage pool. In this chart, in the legend in particular, you can see those pools where the front-end write response time is significantly higher than the expected write response time, and particularly for the Flash and Flash 1 pools. And those are highlighted in bold. We can drill down subsequently on the related volumes and find out additional information. And for the volumes, we can actually get things like read and write transfer sizes and rates and the cache hits. Sometimes we can get information about the replication response time, depending on the platform. So these are all helpful in understanding if there's particular subsets of volumes that have poor performance characteristics, or if they have workloads that are significantly higher than the rest of the volumes in the storage. This is a sample of volume front-end write response time for a number of EMC volumes. All of these volumes have poor response time, and the response time are consistently above the expected thresholds. In this section, we're going to discuss the different types of measurement techniques that are available.
Over the last few years, there's been a lot of improvements in the way that you can get data. There's actually several ways you can get data. You can get data through CLI. You can get data through standards such as SMIS. They all have their pros and cons. The advantage of like a CLI or a native proprietary approach is that there's no programming required. You can simply figure out what commands you need and wrap some shell scripts around those commands to execute those commands on a regular interval. They're also very good at platform-specific support. So any features that are required that you want to report on or get information about, the native tools tend to have those commands available when the new features are generally available. In terms of the code reuse, though, the native commands tend to not be things that you can reuse across platforms. So the commands are specific to the platform. You may have some wrapper code that you execute the commands from, and that wrapper code can actually be reused in some cases. As far as ease of access, it's very easy to use the proprietary CLI commands, the native CLI commands. In terms of standards, there is programming required to implement the standards-based method, which is SMIS. And in terms of the platform-specific support, it's not required as part of this standard, but most vendors have implemented some platform-specific extensions to support features that are unique to their storage platform. In terms of code reusability, the advantage of using a standard is that you do actually get to reuse a lot of your code. In terms of ease of use, from the point of view of a developer, the standards are fairly complicated, but from the point of use of an end user, the standards are fairly simple.
Let's take a look at the SMIS standards. SMIS is a vendor-independent protocol for managing storage subsystems and storage area network infrastructure. What it does is it defines a method for the interoperable management of heterogeneous storage area network and describes the information available to a WBEM client from an SMIS-compliant SIM server and an object-oriented XML-based messaging-based interface designed to support the specific requirements of managing devices in and through SANs. How is SMIS data stored and measured? Well, metrics are stored as monotonically incrementing counters. They're usually stored as 64-bit integers. As such, values can wrap, and collectors of the data must navigate this pitfall. Let's take a look at how this works in real life. Let's say we do a read, and we sample it at time 1, and there's 100 reads. A second passes, and during that second, 5 IOs happen. Then we take a read count at time 2, and it's 105. It's increased by the 5 IOs that have happened. To calculate the IO rate, the collector would need to look at the read count at time 2 and the read count at time 1 and calculate the delta and divide by the number of seconds in the interval. The following table describes how Little's Law
and basic math are used to calculate different types of rates and metrics, such as utilization, response times, and queue depths. It's important to understand that different vendors have different interpretations of the measurements, so it's important to know what those mean before you do your calculations. Most platforms provide both a native CLI interface to gather statistics and configuration information, as well as a Restful API. In the table, I've attempted to identify all of the platforms that support the Restful API. The Restful API is based on a web-based get-post syntax and is useful in integration with other web applications that may exist on your infrastructure. So how do you decide which proprietary option is the best? Well, let's take a look at a few of the attributes that differentiate the two options. In terms of documentation, the CLI implementation is very mature across all platforms, and there's a tremendous amount of documentation describing the commands and the results. Whereas the Restful API, the documentation is fairly limited and developing as we speak. In terms of ease of use, the CLI is very mature and fairly easy for the layman to use without significant investment in time. Whereas the Restful API requires some development knowledge, at least in terms of web development. Regarding security, a user and password is required for most CLI commands, and that requirement is the same on the Restful API. Usually there's not much difference. In terms of the longevity, and what I mean by longevity is how long will it be in the marketplace, the CLI will be there as long as the platform exists. The Restful API is the hot API right now. It may not last forever. And in terms of the requiring an agent, they are both agentless. How is the storage system data typically reported via the native interfaces? Typically, the internal counters are hidden from users. Instead, an instantaneous rate is provided. Rates may be calculated or instantaneous from a user-defined interval. Counters are not always kept in the kernel. For example, the IBM XIB port stats do contain an instantaneous calculation, but they do not keep track of counters. So averages must be gathered over a period of time. The challenge here is trying to find the right balance between ease of use and accuracy. If you don't keep track of every single event that happens and you're only sampling at specific intervals, you may miss part of the story. In summary, storage performance management includes measurement of host I/O, fabric, and storage systems. There are native, vendor, and standard-based tools available for every operating system, storage fabric vendor, and storage system platform. Measurement of key components is critical to the analysis of storage performance management. SMIS is a robust vendor-neutral specification, but it is not able to solve all measurement issues, and it does provide only a subset of what is available via the native interfaces. If you have any questions, please send them to support@IntelliMagic.com. Thanks for listening. I hope it was enjoyable and informative.